Good afternoon, everyone, and welcome to the third round and last of the webinar series, Resilience in Action. Um, we touch base here with relevant research that helps and support the development of drought resilience in farming. I'm your host, Franco Renteria, proudly presenting as faculty group member and node lead of the Drought Hub Eastern Wheatbelt region. Um, just for you to know, the Drought project is led by the Grow Group Alliance, UGA, who hosted yesterday the first Drought Resilience Showcase here in Western Australia. It was a magnificent event with many initiatives and professionals involved in this relevant topic of drought resilience who share expertise and experiences together. We are thrilled to have today Samantha Viljoen, who presented yesterday in the showcase and will deliver today an overview of the Smart Sprays project in his mission to improve soil water retention. Also with us is Tona Sanchez-Palacios, who's going to present what are the benefits of zinc biofortification on wheat grain quality. Thank you both for being here today. I know that it's a pretty busy time of the year. And I want to say that on a personal note, I have a really deep interest in to explore how the applications that you are researching might improve plant establishment and yield. So on that note, I would like to hear a little bit about all of you that are here today in the webinar. What do you hope to gain from these topics? So if you feel comfortable, please unmute yourself and share a couple of words with us. Where you come from, what are your interests? So yeah, and no pressure if you cannot talk at the moment. We know that you might be doing something and you're not able, maybe you're in the car, just checking ahead, and not able to talk. That's okay. So I would like to just encourage Chloe, if you can give us a couple of words and present yourself. Chloe, are you here? Might be Chloe not be able to just unmute herself, and that's okay. What about you, Ravi? Can you give us a couple of words and introduce yourself?
Can you hear me?
Yep. Yeah, we hear you perfectly.
Yeah. So I'm Ravi Parmar. I work as an agriculture project coordinator in FACI group as well. And excited to hear you guys, Tona and Samantha, today to learn more about smart spray. Yeah. Thank you. Looking forward to you guys.
Thank you for that, Ravi. Again, I do encourage you to just turn on your video, and also just a quick reminder that any question that you would like to have, just please, you can pop it in the chat, or you can just hold it to yourself to the Q&A. That's going to be at the end of both presentations. Okay, so Samantha, you can start sharing. I will just give a quick introduction to our first speaker. So today we're going to have Samantha, who is a researcher in Bioplastic Innovation Hub and Soil Waste at Murdoch University, specialized in bioplastic degradation and its impact on soil health. Her work advanced sustainable agricultural plastics, promoting soil sustainability and environmental impact reduction. So Samantha, what is a Smart Spray value proposition? Please.
Sorry, was that a question, or do you want me to start the presentation?
Please, you can start your presentation.
Okay, cool. Sorry. Well, thank you for the introduction. My name is Samantha, and I am a PhD student here at Murdoch University, a part of the Bioplastics Innovation Hub. And like Franco said, I'm here to talk about our new idea that we've got brewing about around the idea of smart sprays. So this is funded by a lot of people, and we appreciate all the collaboration that goes into doing this one project. Cool. So in WA, specifically our southwest region of Australia, which is down here in the green, it is predominantly broadacre crop. And we, in WA, account for 45% of Australia's broadacre crop. But this area is not high rainfall. Since the 1970s, there has been a 15% decline in total rainfall. So if you can see over in the picture on the right, there is the dotted lines showing where it used to rain up until the 1900s, in the 1900s, and then the solid lines are how it's been reduced to the 2000s. So it's also predicted that by 2050, there's also a further decline in rainfall events by 11%. So what does this mean? When it does rain, few and far between, how is our plants and our crops actually using this rain? So a lot of the rain is actually lost. So all the water source that comes down, 60% of that is lost to evaporation, and between 5 and 20% is lost between runoff and drainage through the soil system. Depending on the soil type, obviously between gravelly and sandy soils, the percentage of runoff and drainage changes. So of this minimum 20% left, actually only 54% of that is being utilized by our plants. That means only a fraction of water that is of the rain that is used is actually being used by our plants, going in and generating crops. So what at Smart Spray idea is our fundamental goal is to try and see how we can take this loss of rainfall and convert it into a sustainable product, and how can we take agriculture and take that decline in rainfall through to retaining and using that rain as best as we can. So the current practice that we have globally is using mulching. So this is where we can harvest water from our mounds into our furrows. So we're directing it from, if you're following the blue lines, into our root, retain it in the root system, and also helps reduce evaporation. So typically that is done through plastic mulching. So mostly, however, this plastic mulching is mostly synthetic. There's a high cost to applying it. It's predominantly non-biodegradable. It's difficult to remove once it's been out in the soil, been out into the paddocks, and it's then starting to degrade. It's really hard to mechanically remove, and that means it's also leaving a large amount of legacy plastics or microplastics into the soil. So this is just not ideal with broadacre cropping, because just too much money, too much time, and too much material goes into putting it out there. It doesn't last long. I ran a field trial as part of one of my my PhD, looking at mulch films and how they degrade in our wheat belt, and they pretty much degrade rapidly and leave a lot of plastic waste. So what we have come up with as an idea, or the idea behind it, is using a spray instead. So this spray is made from 100% biodegradable plant materials, and that's this mixture in the middle that's kind of been handed to us, that we would, we'd replace the mulching with, or the plastic mulching films with this spray. So we'll be spraying onto the mounds to, again, direct the water into the furrows to retain it in that root soil. So what the great idea of that is, because it's 100% plant-based and it is biodegradable, it's leaving no plastic legacy behind. That means we're also having an influx of carbon into the soil, which will help regenerate our soil nutrient cycling, because it will just give a kickstart to all the organic material that's in there already, or bacteria that's in there already. So the whole point of it, the spray, is to design it to go from the mounds into the furrows where the root system is most active and where we want the water. So we've got a quick video here of where I've dyed the film blue so we can see it, and then the water goes, as we're spraying onto the mounds, into the furrows. I feel like I keep repeating that, but that's the main point of what we're trying to do, is get the water where we want it to be so it can be utilized by our plants the most effectively. So the future of the smart sprays is like I said, we're very grassroots, very early stages of this this idea, still conceptualizing what we can do. We have been handed a non-commercial spray from our industry partners that we're using to demonstrate the idea and the concept of smart sprays. Because what we want is to just gain interest of what our growers are interested in. If this is something that they think they can utilize, if this is a benefit to them, they even have ideas of like how else we can adapt it, that would be great. So for our period of time, what we're doing now is only focusing in on smart spray that we've been handed by our industry partners and just assess the idea if it's actually effective at improving our water use efficiency. So reducing that evaporation from soil and also maintaining water. So reducing the evaporation and then just guiding the water where we want to go into the furrows. We have conducted some lab scale assessment of it, and early results are promising, but more work needs to go into it. And we are looking at upscaling to our field trial, but site and location is still to be determined. Yeah, that's, I guess, what to come. And it's just, again, getting the message out there, seeing if growers are interested, understanding if this is what they want to do. Big picture, blue sky idea would be able to just take this product and incorporate it into like a spray equipment on the farm, so they can just put it out there when they're just spraying their pesticides or herbicides. They're also adding this spray to help retain water. So this is also a slow-mo of another idea of what we can do is just use it for dust suppression. Sorry, there's a bit of noise in the slow-mo. So as you can see on the left, there is no spray, so it's basically not being able to suppress the dust, and on the right there is a spray, so no dust movement is happening. So that's just one idea that stemmed from this project, but there's multiple more. And like I said, if you guys have any ideas of what we can use it for, that's great. So yeah, thank you for listening. The person who knows more about this and all the ideas behind it is Professor Daniel Murphy here at Murdoch. So I've put his email up there for you guys to get in contact with him. And we also have on the GGA website, we have a whole webpage dedicated to the smart sprays. So yeah, that's the idea behind the smart sprays. Quick and easy stop. Yeah.
Yeah, thank you very much, Samantha. That was super interesting. And in a personal note, this is the second time that I listened to your presentation, and it doesn't stop to surprise me how many things you can do with an innovative idea. We
Yeah.
definitely gonna tune in and look forward how it develops and see what are the next steps on the project. Demonstrations are definitely the thing to go, and the interest will be raised depending on how it's gonna be. So thank you very much again, Samantha.
Thank you.
And I would like to smoothly transition to Tona. So Tona, you might be able to share as well while I do your bio presentation. So I'm really pleased to introduce Tona. He's a lecturer and researcher at Murdoch University, Food Future Institute, specializing in plant nutrition and innovative agronomic solutions. So he focused his work in enhancing grain stability and wheat quality to meet future climate challenges. The stage is all yours.
Thank you very much for the introduction, and yeah, thanks for the opportunity from the FACEIT group to talk about the project that I've been involved in the last 3 years. And yeah, so this project is fully funded by GIDC, and it has the focus on understanding our knowledge about the mineral nutrition in wheat, especially the concentration of macronutrients in the grain, and see how we can improve or correct some of the levels of these macronutrients in the wheat that we produce. So just to give a brief description of how we're going to run through the presentation, I'm going to give you a small background about myself. I'm going to talk about the project justifications of what we do in this project, and I'm going to give you 2 examples of field trials and 1 example of glasshouse studies conducted here in Western Australia. And I'm going to talk in detail about the methodology, the approach, what is the component of innovation with results and some final remarks. So just talk it briefly about me. So originally I'm from Mexico. I come from a place that is very close to CIMMYT. So CIMMYT is an international Center for Improvement of Wheat and Corn. And I found my way to come all the way here to Australia to do some postgraduate studies. And in that process, I guess I've been involved in agronomic process and all the process of phytoremediations that has to do with understanding the tolerance to heavy metals, especially arsenic in eucalyptus, used for mansard rehabilitation. Also been doing some projects that has to do with genetic modifications and editing of cereals to be able to increase the levels of macronutrients for human nutrition. And also been working on projects on hemp and using hemp, which is a fast-growing crop for mansard rehabilitation in Canberra. And recently, 3 years ago, I was appointed to move to Western Australia, moved to Murdoch University, and work on developing some agronomic methods to increase the levels of macronutrients in wheat. Just to start with the justification of the project, we need to take into account that the world population is increasing exponentially, and we expect us to reach 10 billion people by the end of this century. And with that comes the high pressure of increasing fruit production. When it comes to wheat, nearly 20%, and in some cases 50% or more, wheat contributes to the calorie intake in humans, depending on the country. And it's expected that countries in Africa and Asia, they're going to increase their demands for wheat. So the wheat productions, we mainly use it for food consumption is nearly 68%. The second use of wheat is for animal feed, 21%. The rest we use it for seed, as a seed ball can grow more wheat. Biofuel, a small percentage, and other uses. So primarily the use for wheat is for food consumption. So there is a big demand for continue the production and increase even more in the upcoming decades. And so that's clear that we need to increase the quantity, but also we need to take into account the quality of the wheat that we consume. And that's for a very good reason. So historically, there's been some studies done in the UK where they have measured the levels of macronutrients and how the levels of macronutrients have changed over time, especially the levels of macronutrients once the introduction of fertilizers were introduced in agronomic settings. And we can see here in the graph. So once the fertilizers practices were introduced in the 1960s with the Green Revolutions, you can see a big spike of grain yield. Also, this grain yield, as you know, with the harvest index, you can see that production of biomass gets translated into the grain. So we've been having the high yielding varieties since the Green Revolution. Now, if you compare this with the levels of macronutrients, especially zinc and iron, for instance, zinc on the left and iron on the right, you can see that on the introduction of fertilizers, the concentration of these elements in the grain has been decreasing. And if you compare zinc compared to iron, you can see the zinc is decreasing rapidly, more rapidly compared to iron. So the dotted red lines, that is the recommended 45 milligrams per kilogram concentration of zinc that is recommended by the World Health Organization. And it's a recommendation based on countries that they relied on wheat as the primary caloric intake. And that is with the purpose of reducing the risk of zinc deficiency. So there's a big gap in trying to restore these concentrations and new varieties. And so the impact of that globally, so it's a global problem, having a grain produced with low levels of zinc, because that causes zinc deficiency, and in some cases, there's a large percentage of people that are at risk of zinc deficiency. Most of these countries that are at risk is developing countries, and therefore they have been adjusted the way they grow food to be able to provide food with high concentration of zinc. In some cases, they introduce intervention strategies. They provide with supplements to the populations, but the supplements strategy is relatively expensive, and for the long term is unsustainable. They have also tested the fortification of food, so be able to put the zinc into the flour, for instance, and produce bread or produce noodles in that with high concentration of zinc, but the forms of zinc that is provided is not 100% available for the human absorption. So another method, which is the process of biofortification, has been able to grow plants that have the ability to increase the uptake of zinc into the plant tissues and then retranslocate this to the grains during the grain filling. And the theory behind is that this form of zinc in the grains, they're more accessible for the human to absorb it and get that nutrition compared to other strategies. So here in Australia, we don't have the problem of zinc deficiency. It's not widespread. However, our consumers, the people that we export the grains, they suffer from zinc deficiency, especially China, also, India and Pakistan. So as a response, there is international organizations such as Harvest Plus and CIMMYT that they've been developing varieties that are high in zinc and other macronutrients. And they're in the process of testing, and they have already released some of these varieties. For instance, in Mexico, there is varieties high in zinc that has been released, and also India and Pakistan and parts of Brazil. There's other parts in the world that are testing these varieties to see how they perform under those agroecological conditions. But it is expected that in about 10 years, all the seeds produced by CIMMYT or the institutions, international institutions, they will have some level of macronutrient improvement. So from that point of view, here in Australia, then we would like to know well, what's the concentration of macronutrients that we have in the grain that we produce, and how does that compare with that global lines? And this is important because recently Pakistan has managed to produce 15 million metric tons of biofortified wheat with zinc, and that has been a great achievement to be able to scale up these productions at a country size. And it's very successful, this program, and it's expected that in the future, if they continue with these large productions of improved wheat, it's expected that this wheat at some point is going to reach the global market. And then if that's the case, it will be interesting to see if there is a price signal for zinc, if they manage to get a premium value for that. And if that's the case, we want to know how the Australian wheat it will compare to that. So in that regard, so part of the project, we have access to nearly 250 MBT sites across Australia over 5 years. We collected wheat grains, one of the most popular varieties around Australia called Septa. And then we collect this grain, we send it for analytical analysis at the commercial lab, certified techniques, CSDP, to be able to understand well, what is the benchmark for zinc in the Australian wheat over those years. And after that, we did more analysis at the Australian synchrotrons to try to understand where these levels of zinc are in the grain. And so just to give you the results of this analysis, so this is the concentration of zinc in the grain milligrams per kilograms. And then you can see a box plot graph for these 5 years from 2016 to 2021. Unfortunately, we were unable to obtain grain from 2019 due to logistics. But we were able to obtain grains from the 5 years and for different multiple MBT sites. And the mean values is represented in the dotted red lines. And you can see that for all this year, the concentration of zinc is pretty much below 20 milligrams per kilograms. So how does it compare with previous studies conducted in Australia? Well, we have evidence from previous decades in Australia when they measured the levels of zinc, and they were reported in the IPN-NI report, also funded by GRDC. And you can see that in general, the levels of zinc has been low historically in Australia. The reason for that is because our soils are relatively poor in macronutrients, especially zinc. And yeah, so they remain low over time. So how do they compare with international markets? Well, if you compare it to Europe, they have been producing wheat grains with 25 milligrams per kilogram, so we're still below that. Africa's a little bit higher, 29 milligrams per kilogram. And Asia, North America, they're reaching 34 milligrams per kilograms. So it's relatively higher compared to the Australian grain. Most of the grains globally, the mean value is below the recommended World Health Organization target of 45 milligrams per kilograms. And then so they're doing the best efforts to try and to close that gap. When it comes to the Australian grain, again, we have a big gap to close. And so part of this project is be able to close that gap. As I've mentioned before, we have used studies at the Australian synchrotrons to be able to visualize, to see what is the distribution of zinc in the grain. And to our surprise is if we compare it, so what you're seeing here on the right is a cross-section of the grain, and then you can see the distribution of three elements. So zinc is in red, and you can see that primarily zinc is allocated to the embryo very much, and the aileron. And then these parts of the grains that usually are removed during the process of milling. And the part of the grain, the inside of the part of the grain that forms the flour, it's usually deprived or it doesn't contain any zinc. And then regardless of the concentration of zinc that you can see, so on the left you can see a grain that has 7.8 milligrams per kilogram of zinc versus one that has 31 milligrams per kilogram. So you can see the distribution of zinc doesn't change, so it remains primarily distributed in the embryo. So this really dictates that in terms of increasing the levels of zinc, we need to make sure that we can target parts of the grains that can end up in the white flour, and that is inside the grain. So based on those results, and knowing there's a big gap, we ask, in general, the question is, well, can we correct those levels of zinc in Australian grain? And can we do that by using agronomic methods in comparison of using genetics or using lines that could potentially take a decade to develop and test? And then, so this is the big questions, and I guess our approach is, well, developing agronomic methods, especially focusing on liquid fertilizers to apply foliarly, to test conventional zinc foliar products on Australian wheat, being able to innovate these foliar formulations by increasing the efficacy or efficiency, also conduct analytical techniques that we can get some confirmations that these products are improving the quality of the grain, and most important, see how much of that zinc, if we manage to increase the levels in the grain, be translated into end user products such as bread and noodles. So just to give you the first example about the field trials, we have conducted studies at the Wongan Hill Research Station in collaboration with the Department of Primary Industries. Those are really good locations because we can see that that soil, you can see that you have adequate levels of zinc on the topsoil, but once you pass the 10 centimeters of topsoil, you really find deficient levels of zinc in the subsoil. You can see that the plants, when they grow, they show some marginal levels of deficiency of zinc, but they recover over time. The approach is doing foliar applications, applying, and it's important in terms of the sprays to take into account to use the right source, the right rate, the right placements, and the right timing. If you get one of those ones right, your approach, well, it's not effective pretty much. So for these experiments, we applied a control and we tested two different forms of zinc. One is zinc sulfate, which is cheap and is available for farmers. Zinc 88 is a chelated form of zinc. It's more expensive, but it's a form of zinc as well, and you can find it in agronomic settings in some managements of fertilizers. Within the formulations, we applied two different levels of nutrients, so one with nutrients and one without nutrients, and we apply this as a stimulants. So we apply 3 treatments. We apply 2 levels of zinc, and we have 5 replicates per treatment. The rates, we did 4 foliar applications, each one's at 1 kilograms per hectare. And we did it for a manual spray. So we target 4 stages. So we went from mid-flowerings to all the way to mid-grain filling. Yeah, and we were targeting this stage because it's the time of the plants that increase remobilization of proteins and macronutrients into the grain. So the approach is we prepare the foliar formulations in the lab. We go to the field, we apply it in the afternoon to be able to reduce any risk of burning on the plants and also wind. At the end of the season, we harvest the grains, we clean it carefully, we send this grain for analysis to CSVP. We do elemental mapping analysis, as the ones that I showed you before at the Australian synchrotron. And then we send the grains to AGIC, which is a collaborator. They do the grain quality studies. They do the milling, they produce the white flour, and they can produce bread and noodles. And then we send this end product for analysis to another facility, and then we get the results. And then we evaluate what is the effect of applying the foliar formulations. So here is a table that you can see. We have the T treatments, control, zinc EDTA, zinc sulfate, without nutrient and with nutrient. And if you look at the grain zinc concentrations, you can see the control of zinc in the control is around 13, 14 milligrams per kilograms with or without nutrient. And that's not a surprise because that's usually the levels that we find in the MBT side, so below the 20 milligrams per kilograms. Once you treat the plants with zinc EDTA, zinc sulfate, you can see an increase on both treatments, but you can see statistically significant differences with zinc sulfate compared to zinc EDTA. So that's the good news because in terms of zinc source, zinc sulfate is cheaper compared to zinc EDTA, and it's good that we can get increase those levels of zinc in the grade substantially compared to the control. So once we look at the white bread increase in terms of the concentration, you can see the control it retains some of the zinc, but once you compare it with zinc sulfate, you can see that we increase in the concentrations of zinc twofold increase. When it comes to noodles, the noodles is quite interesting because you can produce the noodles and they are uncooked initially, and then we can measure the levels of zinc in there. And as you can see, the levels of zinc in the control is around 2.4 milligrams per kilograms, so significantly less compared to bread when they're raw. Zinc sulfate, it has 3 times the concentration of zinc in there. And then most importantly, once you cook, you can see that is effect of leaching of zinc. And then so the concentration of zinc it usually decreases. So for the control went down to 1.5 milligrams per kilograms. And surprisingly for the zinc sulfate treatments, the concentration went low, but also remained higher compared to the control, so twice as much. So it's a very interesting results here and effective with the foliar application. So then we took the grain to the Australian synchrotron, which is a facility that's able to produce a very bright light and produce X-rays that you can actually see the atoms inside tissues, and you're able to collect information from a very small area of the sample. And then if you collected information from that small area, you're able to build a big picture of where this concentration of elements are. So we apply that technique to our grains that we cultivated in Wongan Hills. And here's what they look like. So for instance, at the top, you can see the grains as we position the grains before analysis. Then you can see this is an elemental map for zinc. So you can see where the zinc is. And then just below, I just reorganized the grains based on the treatments I already showed you the concentrations of. So you have the control, the zinc EDTA, and zinc sulfate. So it's not surprising to see that the reason why we're able to have more zinc in the zinc sulfate treatments compared to the zinc EDTA is because there's more zinc on the endosperm of the on the grain, which is the part inside of the grain. So that's good confirmation of the efficacy of the foliar fertilizers, conventional forms of zinc. So in addition to that, then we ask the question, then can we improve the efficiency of these things by adding, putting other additives in the formulation? So for that, we conducted experiments in the glass house, so control settings. So we developed the foliar formulations in the lab. We used the facilities at Murdoch University. We spray the plants following the same protocol that I showed before, mid-flowering all the way to grain filling. We harvest the plants, we collect the grains, we send it to CSVP for elemental analysis. The plants, the individuals that are most interesting, then we collect those grains and we go back to the Australian synchrotrons to do more elemental mapping analysis. And in a nutshell, what you can see here, well, you can see here the elemental mass for zinc again, and then you can see the treatments that we perform in the glasshouse. So on the left, you have the control. So it's interesting to see the concentration of zinc on the control conditions that are a little bit higher compared to the MBT side, so about the 20 milligrams per kilograms. And the reason for that is because we grow the plants under optimal conditions. And then so the soil has enough zinc. So you can see an increase in the concentration of zinc. Regardless of that, once you apply the foliar zinc, which is for zinc sulfate or zinc EDTA, you can see that it's an increase. So zinc sulfate, 48 milligrams per kilograms, and zinc EDTA 41. So you can see the same trend even in the control settings, that the treatment of zinc sulfate is slightly higher compared to zinc EDTA. Once you compare it with the new foliar formulations, you can see the concentration is high, especially with the zinc lipid chelator. And then you can see that the distribution of zinc, it remains high in the embryo, but you can see that also you have high signals inside the grains, which is really good news for the biofortification outcome. Once we compare zinc nanoparticles, zinc oxide nanoparticles, this is quite interesting because in agriculture has been a big interest on using zinc metal nanoparticles, zinc nanoparticles as an effective way to biofortify the grains. But based on our results, the zinc oxide nanoparticles, they were not any better compared to zinc sulfate. And that's important to make that distinction because zinc nanoparticles are expensive to produce. And then the fact that they didn't do better than the zinc sulfate, that means that you can still use a cheap form of zinc to obtain the same or even higher concentration of zinc. The grain on the right, which is the zinc silicon nanoparticles, is the ones that produce very good results. Yeah, we're able to see that the concentration of zinc went to the embryo, but also inside of the grain in the endosperm, which is a really good outcome for the project. Yeah, and then the last experiments that I would like to talk about is experiments that we conducted last year in Pizarra. And this is quite significant and eye-opening to us because that year, the 2023, it got a hot, dry end of the season. And that really affected the flowering and the grain filling stages. And we saw that. And when we saw that, so we applied our protocol of foliar displays. And then we saw that once you have those sort of conditions, hot and dry conditions, the effect of the foliar applications regarding different doses and apply and targeting different stages, whether if it's flowering or grain fillings, they cancel out. So in that regard, you can't apply only just 2 kilograms per hectare and start getting the same outcome if you were applying twice as much zinc in the system. So in this case, 4 kilograms per kilogram. So it really depends on the forecast conditions for the end of the seasons to adjust this approach and be able to, if you have a hot dry end of the seasons, you can apply just 1 or 2 kilograms of zinc sulfate and obtain the same results in comparison if you were applying 4 kilograms per hectare. So it's something that is important to consider for future practices if the farmers adopt this technique. And in conclusions, based on the results, so the foliar zinc applications with the stimulants, they were quite effective, so they were able to produce grains with high zinc, and they get translated into the end products. What is next is, well, of course, we would like to use these foliar fertilizers to apply it during the vegetative growth to see if we can get a response on biomass productions, and most importantly, to see if we can actually increase yield on wheat. Also, we would like to scale up this technique, and by doing that, we need to reduce cost, and for that, we need to use potent biostimulants that can increase efficiency even more. We would like to use X-ray fluorescence instruments that are more accessible, and you can access in a lab rather than just going to the synchrotron, so you can analyze more samples. We also would like to include drone technology for 2 reasons. One is to deliver the foliar fertilizers, but also to use the cameras and be able to see if you can measure the response of the plants to the foliar application. And also another aspect that we would like to consider is testing with cultivars, different wood cultivars that can have a positive response to the foliar applications and the stimulants. And and I would like to thank the project manager, Professor Richard Bell, that he was the project manager of this project, and all the collaborators, the people from GRC, for ANSTO, at the Australian Synchrotron, the Department of Primary Industries, the people from EGIC, and all the collaborators from Murdoch University. If you want additional information about these projects, we have also done experiments using isotope tracing analysis at the Lucas High facility in Sydney. And then so you can find more information online about the type of experiments that we're doing. And that's all for me. So thank you very much for your attention, and I'm happy to answer any questions.
Thank you very much, Tona. It's actually really interesting. We had touched base in the WHEAT conference with biofortification opportunities and what other countries and researchers have been doing in this stage, as we have touched base with what South America and Africa has been raising their interest. As we still have the opportunity, there is this trade export potential opportunity to get there if we just manage to get that level of quality in already a market that is rising, which is actually, I reckon that one of our takeaways. I have a couple of personal questions, but I would like to just kickstart our Q&A. If anyone has any question for our presenters, please feel free to unmute it or just check it in the chat. And they are really keen just to give us the most accurate answer that they can, though. I just add some information regarding Tona's research and as well Samantha's project for you to check. There are other links, and as well the YouTube channel where you can see this recording and the previous recordings of the webinar. I would like to maybe I can start if you allow me. I have a question that I've been holding it for Samantha first, if you allow me, Tona. So, Samantha, yeah, thank you. Yeah, I did have. I reckon there is a lot of open opportunities with what you can do with that biopolymer. Uh, I was trying to see how I understand how the potential benefits. Have you touched base with potential constraints that could be related to the use of the same product? Talking about potential water repellents or how that can actually be tackled down in that sense.
Sorry, just can you rephrase your question?
Yeah, sure. So from a practical aspect, do you consider any, because you haven't done any demonstration in the field, but on the lab, have you tried to test what will happen if you could create potential water retention? Because at the end, you want to retain as much water in adequate parts of the soil so the plant can access to it. Does the polymer also create other constraints, or are just those benefits the ones that are sitting down?
So the idea behind this project is there's no actual R&D in this. So we've been handed this project, asked to test it and just prove the concept of it. So I do see, like, I envision that more development of the project can happen in the future, but that's outside the scope of what the Drought Hub has funded for us. Potential issues that could come would be that the polymer doesn't actually last as long as we predict it to. We're expecting it to, or we've been told it will last like 6 months, but if it only lasts 3, that means we could be missing them rainfall events that's wanting, which would just be like the soil is no change. Another issue I know that could happen is that because our soil here in WA is so variable, we'd actually have to put a lot of engineering into the spray to design it for each type of soil. So one type of soil might like one polymer, another type of soil might like another. So it's not like a set thing, but like I say, that's kind of like outside of the scope of what we're trying to do at this moment in time. We're just trying to prove that the concept works of trying to retain water use efficiency in the soil rather than like I think in doing that, we're coming up with all these problems or coming up with all these questions that require further work and further funding, more time than what's inside the scope of this project. Yeah.
Yeah, that's a really, really good question. I definitely it need to be tested in that sense as well. But idea is still there, yes,
Yeah.
to be used. And also to have two more questions to follow up. So
Mhm.
Chloe is asking, what plant testing has been conducted with the smart sprays?
So far it's been no plants. We've just used soil and collected from locally around here. I can't remember the region, but we're just seeing if water is able to be retained in the soil, not seeing if that's actually then gone into the plant. I guess that would be the next step that we'll be looking into is how is that water? Is it available for the root system or is it still being lost through drainage? But right now we're just focusing on the water use efficiency of the soil.
And on the follow-up on that, Ravi is also asking, do you think that soil temperature is affected by the spray?
I think it would be no more like I don't think it's going to be extremely like this is just my thinking of like my ideas of it. I don't think it will be any more affected than using like plastic mulching. I think it will help more regulate the temperature of the soil so it wouldn't like fluctuate as we have our really hot summers compared to our like freeze thaw winters. So I think it will just help regulate the soil temperature and just provide like a happy environment for the micro like biome to start doing its work and help cycle nutrients.
Yeah. Yeah, thank you very much, Samantha, for asking those questions. I have one for Tona if no one wants to jump in. Um, Tona, so actual research is quite interesting, as I was just touching base with. When you say about the applications of Zinc, I was thinking of how you go deeper in what is the right time for doing the application, what would be the most efficient way to actually get the most benefit of those ones?
Yeah, so we have done experiments when we compared, actually, we have compared the flowering time versus the green filling time. And depending on or how the conditions of the end of the season. So if you have an average or a soft ending of the seasons, we found out that the flowering time is quite effective. So the plants are very receptive of the foliar applications that they're able to load a lot of zinc into the grain. However, if the end of the season is hot and dry and flowering is still probably the best time, but you have a very small window for that. So I guess in future cases, if we're having hard, dried, hot end of the seasons, I guess the window for foliar application it gets smaller in that regard. But that's not a bad thing. Like I guess our practices is being quite. We have done 4 foliar applications, and that implies that it's a lot of labor in that. So ideally, what we like to do is just to come down to just one single foliar application and be able to obtain the same results. Yeah. The only trade-off with that is that you need to be really careful with the concentration of zinc that you apply, because if you apply too high, you get a scorching of the plant material. Yeah. So you don't want to damage the plant materials. However, with the new foliar applications, with the new additives that we applied, that problem is resolved. So the toxicity of zinc is no longer there. So be able to provide the zinc in a different form that it doesn't affect the plant, and actually enters the plants quite rapidly and move very rapidly within the plant body as well. So we would like to. So this is phase 1 of the project, and we've been discussing with JDC potentially having a phase 2. And in this phase 2, we would like to do more extensive field trials and then test a single application and test more new foliar applications that we have in the shelf, and we would like to actually take it out of the shelf and test it in the field. Yeah.
Yeah, that would be fantastic. And definitely, first I want to say thank you both for the clear answers and insightful presentation. We will definitely like to know more what are the next steps and where is actually directing both researches. for the upcoming 2025. And as a matter of closure, for the whole webinar series, I would like to acknowledge the support of Murdoch University, which we have been working really close in multiple research ventures, as well as GTA and the Drought project. And all of you participants has been turning in during the whole webinar series that are actually what it makes this kind of event valuable. Facing Group is always looking forward to keep moving these webinars, Resilience in Actions, in a more safe and valuable space for uh, for you to be able to reach it anytime in the future. To talk a little bit more about drought challenges. So keep following us in 2025. Follow our social media channels, our YouTube channel. Check our newsletter. There are more things coming. And these 3 rounds are going to be as well for you to review it anytime. Once again, thank you for your time, questions, and active participation. We hope to see you again. Have a great evening and enjoy the holidays. Thank you very much all.